Swayam Prabha. Digital India. Educated India.
Last round, you're all surviving, good. So this is the battery part. And here you will see, I think it's a good idea to finish with batteries because you will see a combination of the both things that we've seen so far. So we've seen phase field applied to fracture, and this will be the first part of the presentation. But you will also see that whenever you have an interfacial problem, even if it's a problem that you haven't seen simulated before, you can always develop your own facial model to tackle that problem. And that will be something I'll discuss later on. So again, I think, oh, sorry, it's a bit slow. Yeah, so this is the last part. I'll try to finish in 1 hour and 15 minutes or so. So I don't think the batteries need a lot of motivation. I know some of you are working on this area. I mean, lithium-ion batteries are key to storing energy, and we have them in our phones, in our laptops, and so on. The way they work is relatively simple, just in case someone hasn't seen it before. So a conventional lithium-ion battery, you have basically, every time you charge your battery, you have lithium ions that go from the cathode into the anode, and electrons that go the other way around. And lithium ions, when you discharge, you have lithium ions going from the anode to the cathode. And you can see that the anode and the cathode in conventional lithium-ion batteries, you have an aqueous electrolyte, so it will be a liquid electrolyte, and then you have these particles, these anode storage particles and cathode storage particles. So this will be cylindrical particles, typically NMCs or some sort of ceramic along those lines, and then there will be other phases. There will be some voids, there will be some binders, some fillers, and so on. But the main problem is that these lithium ions, what they do is they get stored. That's why they call it storage particles. They get stored in those particles. So the lithium ions that go, every time you charge your battery, you have lithium ions that go from here all the way to here, and they get stored in these anode storage particles through a process called lithiation. And every time you discharge your battery, you get these lithium ions that are released from those particles and then come here to the cathode particles. And this lithiation process, this storage of lithium in these particles, what makes those particles is change volume, basically. They swell and shrink. So basically, they're going to change. There's going to be some chemical strains that I'll discuss in a minute. And the continuous swelling and shrinking of those particles leads to cracks. Remember, these are NMC, these are typically ceramic materials, so they're going to be more prone to cracking. This is what you see here. This is an SEM image of one of those cathode storage particles, and you can see, and you can see actually that is, cracks seem to appear again in the grain boundaries, right? So there seems to be some sort of macrostructural sensitivity there. So swelling and shrinking of particles is a cyclic process, and you generate those cracks. So of course we thought, why don't we use, the multi-physics phase field technologies that we have developed to tackle that problem, basically, to predict when failure will happen. And again, throughout my course, particularly when talking about some of these engineering applications and developing multi-physics phase field model for these engineering applications, throughout my research and throughout the course and throughout the seminar, I always like to emphasize the key point that the goal here with these models is to basically understand behavior, predict safe regimes of operation, under what conditions will those particles do not exhibit cracks. So then engineers know, how much they need to charge or discharge the batteries, but also, develop tools that allows us to quickly test solutions, basically, to provide answers to the problem. And I should say, in hydrogen, we were the first to develop these phase field hydrogen technologies, but in lithium-ion batteries, there had been other groups that had already simulated phase field and lithium-ion or electroparticle cracking. So both cathode and anode are electrodes, for those of you not familiar with this. So electroparticle cracking had already been simulated with lithium ions and phase field, but they had only been simulated for a half a cycle because they didn't have fatigue, so they couldn't simulate the accumulation of damage that you get when you do cyclic loading. So this is what we decided to do. But before I get into the fatigue part, let me just tell you that the problem is very, very similar to the hydrogen problem that you heard about a million times now. So you have a displacement field coupled with a phase field. Again, now it's phase field fracture. I'm interested in phase field fracture. I'm using the phase field to describe how cracks develop within my particle. So you have a displacement field. Then you have an equation for the evolution of damage or for the evolution of the phase field. Remember, this is the same as usual, the strain, the density, and the energy. Then you have a transport equation for the evolution of, for the transport of lithium, identical to the one of hydrogen. But then there's a few other items. So there's this extra item here. So there is some chemical strengths. And these chemical strengths are driven by, change in concentration. And these chemical strengths are also present in hydrogen. But because the partial molar volume of hydrogen in metals is so small, these chemical strengths are tiny in hydrogen. And you can see that, the models naturally capture these things because they are models that rely on physical parameters. So we know what is the partial molar volume. Sometimes we call it VH in the hydrogen problem. So we know what is the number of this. We know that in hydrogen is 2 centimeters mole, here is 13. So because we know the numbers of these values, these phenomena that we see in the experiments come naturally out of the model. You have a model that relies on physical properties. So on hydrogen, I know this is 2 centimeters cubic per mole, so it's an order of magnitude smaller. So these chemical strengths are quite small. Here in lithium, these chemical strengths, because this is bigger, they become much larger. And then the other thing is that this fractal energy, this toughness, does not depend on the lithium concentration. Hydrogen really changes dramatically. This lithium doesn't change that much. There's a paper of Bill Curtin using atomistics where they see a little bit of a degradation, but it's very small. So you can neglect that thing, I think, as a first order approximation. So I've never seen anyone accounting for, but I mean, some atomistic data exists showing that this is a bit dependency on the lithium. So you could do like hydrogen, but much lower. But this is the key element. This in hydrogen is tiny, here is much bigger. And in fact, in these batteries, I mean, it depends on the battery configuration. Sometimes people apply pressures and so on. But in general, you don't think of these batteries as something where you're applying a big mechanical pressures or big mechanical load. So before, we were dealing always with components that were subjected to fatigue, to tensile stresses, and so on. Here, the reason why we see those cracks are these chemical strains. So the battery is not being applied any load, it's just been holding there, but the lithium coming in and out, these lithiation processes brings these chemical strains, and that is the mechanical component that is triggering those cracks, basically. That's the idea. And as I said, some people have already looked into this before. They have looked into idealized particles only, and only a half cycle. Charge or discharge, but only a half cycle because they were not, they were not able to model fatigue in phase field. However, when we look at the data, when people plot, I mean, it is true that the first cycle is important, but when you look at the data, let me plot it here. So when you look at the data, some people, look in the microscope, interrupted tests, and so on. They can quantify. There's some literature on this where they quantify number of cycles, number of cracks in the particle, in the electroparticle versus number of cycles. And it is true that of course, you start in 0, but then in the first cycle, you go all the way here. It's a big jump. These are ceramic materials, so lots of cracks appear at the beginning. And then with cycles, it becomes something like this. So again, we were not the first to simulate fracture in electroparticles. I think maybe the group of Bob McMeekin in UC Santa Barbara was the first. But they look only into this, which is important because you get a big jump already in the first cycle, but then there's other things happening. So we wanted to have a tool that allows us to simulate the full degradation of the battery. And the other thing is that people have looked only into idealized particles, so spherical particles. We wanted to look not only into idealized particles, but also into realistic particles. So we coupled this with XCT scans, and then we were able to predict what happens with these non-idealized realistic particles. Because they try to make them spherical, but they're, it's difficult to manufacture something that is fully spherical. And then you can apply, this cyclic loading of lithiation and dilithiation. You have something that characterizes your load that is called the seed rate, which is kind of the concentration change, the flux that you're getting. So this is the lithiation and dilithiation, and this is basically the number of cycles. And this was done together with a good former colleague at Imperial, Billy Wu, who is a battery expert, and he was the one who suggested doing over 300 cycles or so, which I guess is relevant to, electric vehicles or things like this. I don't know how many cycles, but it is on this order. The order is hundreds of cycles, so we can do those things with phase field models. We can simulate cycle by cycle. And these are some representative results. So here you see, the concentration, distribution of lithium. As the crack grows, you see little crack. The crack has expanded. This is a spherical particle. This is the hydrostatic stress, as a function of the number of cycles. 50 cycles, very little crack growth. 300 cycles, big crack growth, and so on. And in this area is an area where mostly people have done, the only models that were out there were models based on Paris law And the Paris law in these materials was not well understood. The Paris law regime is small in ceramic materials, so you need to understand the crack initiation as well, the stage 1 as well. So I think this all comes in naturally into these models, but it's not captured in those Paris law behavior. And there's also, there's a coupling with the lithium as well, so that's a bit tricky to characterize. But then what we can do, once we have a tool that is able to predict those things, we can do parametric studies, and more details you can find in the paper. But what I want to tell you is that once you have a tool, then you can change the C rate, for example, and determine under what conditions you will not see any cracking, or the particle radius. For example, you can play with the particle radius. And industry is trying to make particles smaller, but there's some issues. There's some challenges on the manufacturing side of things, and there's some other issues that come with having very small particles. And you can see below that particle that we took from the XCT scan with a realistic geometry, realistic defects, how those defects are growing, and how you get quite complicated cracking patterns that you cannot really characterize with Paris law. So reality is much more complicated, but these tools allow you to simulate the reality. Okay, so this is what it refers to single particle phase field fatigue. Everything that has been done so far on phase field multiphysics for batteries have been done on single particle cracking and only 1/2 cycle. The other thing that we did was to extend it to the electrode level. So again, computers are becoming large enough, so why don't we go from single particle to full electrode? So again, this is work together with a good friend of mine, Adam Boyce, and with Paul Schering, who was at UCL but now is at Oxford. And Paul Schering and his groups are experts on XCT technologies, so they were able to obtain very nice images of the entire, not the entire, but the large scale electrode level. So you can have not the full cathode, but a big portion of your cathode, and therefore not only you resolve the particles, but you can also resolve other phases like the pores, the carbon binder. So you can capture interaction between particles, things like electrode thickness, for example. This study was very useful to understand the role of electrode thickness, so we try to incorporate that into the model. But it's the same equations as before. You're solving the transport of lithium, so there's a transport boundary condition where the concentration of flux. You're solving the mechanical deformation problem and then the phase field. And then what you have is different materials. So this is what you see here. The way this works is that you do XCT scans, and either in the synchrotron or in a laptop XCT. Those XCT scans will normally trigger a lot of information, very large files that you need to process. There's multiple ways you can process that. There's a commercial software called Aviso, for example. And then you do some sort of segmentation. There's a lot of people now working actually in machine learning to speed up this process, but basically you treat those images with whatever tool you want. You end up with these segmented images where you have the particle, the carbon binder, and the pores, and then you introduce those. You can directly embed those images with this Aviso system, for example. You can directly bring that into console. You have a mesh in there, and then you run the simulation, and you see the cracks propagating in those particles due to phase field. And then you can predict basically the battery performance. You see here cell voltage versus degree of discharge for various applied potentials. So this is what typical examples. So you can see here the large-scale model where you see cracks starting to develop, and you can see that there is some sort of heterogeneous mechanical and electrochemical behavior. So this is what we're interested in. People were looking at a single particle, but we know that particles behave very different depending on their location within the electrode, and we were quite interested in knowing the optimal electrode thickness, so to say. But here you can see representative examples. So these are the quantities you're solving. You're solving a mechanical problem, so you get some hydrostatic stress that will drive the accumulation of lithium. You get the state of lithiation, the concentration of lithium, and then you get the fracture process itself. So again, a tool that not only is able to simulate one particle, but thanks to the growth of computers, we can simulate things at the electrode scale. So we can understand not only the role of one particle, but also the role of the location of the particle, the role of the geometry of the electrode, and also secondary phases such as voids or binders. That is the idea. But you can also go down the scales. And again, this is work with the same group. They are very good, again, in microscopic, in micro-CT and X-ray diffraction. So they're able to obtain very nice images of the particles. So these are realistic images. So within the electrode, they can see what the cracking process is. And therefore, you're able to see in operando where those cracks will develop within your microstructure. And this is the same as we do in the model. So again, a realistic particle coming from an XCT. We simulate the grains, all in 3D, and then we can predict the evolution of the phase field over the grain boundaries. And here I should say that we have different, again, we use the phase field. So this is similar to the case of composites. So we use the phase field, but any function you allow to interpolate. So if you think of a grain, some sort of grain and some sort of interface, you can always use some sort of function to interpolate the properties between the grain, the bulk, and the neighboring grain. So in this case, we knew that the interface properties, people doing some clever experiments on trying to determine some sort of interface toughness. So we could introduce the interface toughness of these grains, and then we were able to see, very similar to what we see in the XCT scans, in situ, what was the growth of cracks within the particle. Aspects that, okay, why do you care about this? So here, as I said, one of the options is, we want to understand the geometry of the electrode. We understand the role that, pores have. Maybe we want to improve our manufacturing process to reduce the pores. Here, in addition to, the mechanistic scientific understanding, what they were hoping to understand is the role of these grain boundaries, in the sense that I think there's a rumor that Tesla was going to come up with a single crystal battery, which will last 1 million cycles or something like this. So this is the idea. How much do we win if we remove, if we assume that the grain boundaries are the weaker interfaces, how much we gain if we remove those things? And we can test those ideas quickly in our model. There's also other people who have suggested the idea of using kind of functionally graded microstructures. So the idea would be that you have the flux on lithium is, of course, the concentration of lithium, the gradient of lithium is very different. So the chemical strengths that you're going to get are very different. So some people argue that maybe you need, imagine the small grains or big grains in the outer boundary, and then this will become smaller as you approach the center of the particle. And there are various approaches where people are trying different things. You can test all of these ideas quickly with this model. This is the idea. So again, trying to understand safe regimes of operation and trying to develop a tool that by resolving the physics of the problem allows you to test ideas quickly. Okay. Yeah.
Is this a two-way coupled problem, or because you don't see change in the elastic stiffness as a function of the concentration?
There is a change in elastic stiffness. Okay. No. Sorry. Yeah. Good point. So coupling is depending on what you're looking at. This coupling. So these are the coupling. So the usual one, the phase field will degrade your balance of linear momentum. The phase field will evolve based on your strains. These strains, you have both elastic and chemical potential and so on. So there will be a change in the stress state that will transfer into the phase field. You have lithium transport that is affected by the mechanical fields. And then you have chemical strains that are affected by the concentration of lithium. So there's a two-way coupling in a way between the mechanical problem and the concentration problem. Mechanical, the hydrostatic stress term. The battery community at the beginning was not incorporating this, but then they saw some experimental evidence of this playing a role. I can't remember exactly what was the observation, but suddenly they all started accounting for this, as opposed to the hydrogen community where we never accounted for this, but we always accounted for this. But in any case, you do have a gradient of hydrostatic stress, so the lithiation is easier when you have lattice expansion, and then you have the chemical strain. In our case, we solve either, for the fatigue problem, we solve either fully coupled, so everything monolithically, but we have also solved problems staggered depending on what. I think for the full electro calculations, it was a bit faster to solve the problem staggered.
But the stiffness itself is still a constant. It's not going to change as a function of the lithium.
No. So the only thing that would change the stiffness will be the phase field.
Yeah. So that's the degradation of the stiffness. But
yeah, they will not be changed. I mean, some people have used phase field to model the lithiation process. So I guess they will see a little bit of change in stiffness. We didn't see that much. However, there was two effects that people reported in the literature that they suspected will play a big role, so we incorporated into our model. One was the diffusivity will be dependent on concentration, and this apparently mattered quite a lot. But also this kind of partial molar volume, which will govern these chemical strengths, will be dependent on concentration. And they can measure this with some GITT experiments and so on. And there we saw a bigger of an effect. But we never, although there's a community doing phase field to model the lithiation process, we never thought there would be much of an effect on the stiffness. So at least we haven't done it yet. Okay, so that is all when it comes to the conventional lithium-ion batteries. And then I spend a bit more time. Any other questions related to the conventional lithium-ion batteries? If not, we're going to move to the all solid-state batteries, which are basically the next big breakthrough in battery technology. So this is what everyone is working on. So I think Toyota made a statement that they will have all solid-state batteries in, I don't know if it's 5 to 10 years, but they made previous statements in the past along those lines, and they haven't always fulfilled those statements. So people have a bit of a skepticism, but they are really a cutting edge in research. I think there's a German automotive company, I can't remember which one, BMW, Mercedes, that recently said that they were already doing some tests with all solid-state batteries. So this is where the technology is going. The reason being is that, well, it's twofold. First is that you will improve safety significantly, because the idea is that you replace your electrolyte, your liquid electrolyte, by a solid electrolyte. This is the idea. And then you remember when you fly or something, they sometimes tell you cannot carry a lot of batteries with you and so on. So it's the same idea. Sometimes they tell you with electric bicycles, you cannot bring electric bicycles into the building. This is something we hear all the time in the universities in the UK, because they're afraid of fires. And there have been some fires and explosions, and this is due to the fact that the liquid electrolyte that we currently have in our laptops, in our phones, is flammable. So by replacing with a solid electrolyte, that's first good news from the safety point of view. But it's also good news from a performance point of view, because if you are able to replace the liquid electrolyte by a solid electrolyte, then you can use lithium metal as the anode. Lithium metal as anode becomes unstable. And then you gain an order of magnitude in capacity. So this is the goal. I mean, an order of magnitude to change. I think I showed you yesterday when I was talking about the multiphysics modeling that this is the main motivation for the solid-state battery community. They say if we don't change the chemistry, we are already pushing our batteries to really the theoretical physiochemical limits. We are really pushing the batteries to their limit. I think I showed you that graph where it was showing kind of the theoretical limits, and we're almost getting there. That's taken actually from, I think I took it from this paper, the Nature Energy paper by Janek and Sear. So the argument of the solid-state battery community is that we cannot improve any further conventional batteries. We need new chemistry, we need new types of batteries, and a more disruptive breakthrough. So everyone seems to agree that all solid-state batteries will be the next big breakthrough in battery technology. And theoretically, it makes sense. You solve the flammability issue, but you also allow to use lithium metal as anode, which will increase capacity by an order of magnitude. So everything looks quite promising. But the problem is that mechanics or materials problems are holding back the commercialization of this battery. So it's been, this is almost 10 years. This was, I think the name of the paper was something like a solid future for solid-state batteries or for batteries or something like this. So scientists have been hoping for 10 years, almost 10 years now, which is it's not a lot in other fields, but the battery technology field is one that is receiving a lot of funding and that is moving quite quickly. So people were already hoping to have these solid-state batteries in the market since some time ago, and we are still being held back. And the reason you're being held back is by mechanical problems or mechanics and materials problems that arise at the interface between the lithium metal and the solid electrolyte. And you can see some of them here. So you have some wetting issues, you have some cracks, you have defects. But more importantly, you have these dendrites. So these dendrites are what you see here, some sort of needle-like structures that appear at the interface between the lithium metal anode and the interface. And then they will grow, they will carry lithium inside, and they will grow all the way to the cathode and basically cause the short circuit of the battery. You bring lithium metal all the way to the cathode, you connect the anode to the cathode, you have short circuit of your battery. And this is the biggest problem, the dendrites. And the people have been trying to fight these dendrites for, again, 10 years at least. And there are various ways when people are trying to find those dendrites. And initially the first, lithium metal is quite soft. It's almost like toothpaste. So people thought, okay, they were using polymer electrolytes, but they said maybe if we replace the polymer electrolytes by more stiffer materials, then we will prevent those dendrites. And then first they needed a breakthrough in electrolyte conductivity, but then they found ceramic electrolytes that were almost as conductive as those polymer electrolytes, so problem solved. And then they were happy, they put those ceramics in it, the dendrites still go through. So people are wondering, how can it be that this toothpaste gets through the way of a stiff ceramic? And there's a lot of discussion on the mechanisms. And a lot of people, I'm not going to touch on that, but a lot of people modeling with phase field those dendrites precisely, the formation of those dendrites and the growth of those dendrites. Maybe I should have included a slide on that. But anyway, it seems that there's no way to stop those dendrites. And this is what you see here. So those black things that you're seeing here, those are the dendrites growing from the anode to the cathode. This is experiments from the group in the University of Michigan. And you see basically that those dendrites nucleate at the top, form at the top, and then they grow until they cause short circuit. So whenever the quickest dendrite reaches the bottom, you get complete short circuit of the battery. So here I'm rotating the battery that before I was showing it in vertical, now I'm showing it horizontal. Dendrites start on here. So there doesn't seem to be a way of stopping those dendrites from growing. And a lot of effort has been put into this, and if we can find a good collaborator of mine, we always said, if we find a material that will prevent those dendrites from growing, material scientists with enough funding, and they'll get enough funding for this problem, will find a material that will prevent those dendrites. But we don't seem to be able to find one. So in my group, we took a step back and we said, okay, if we cannot prevent those dendrites from growing, can we prevent those dendrites from forming in the first place? And how do those dendrites form? Well, if you have a pristine electrolyte electrode interface, so anode electrolyte interface, those dendrites will not form in the first place. So here, what you're showing here, this is the lithium metal, and this is the electrolyte. So again, if I go back to this picture, I'm basically rotating this, right? I'm zooming here, and I'm rotating this. So if you have something like this, lithium metal and electrolyte, that would be great. There's nothing generating those dendrites. The problem is, life is never perfect, so your interfaces are never going to be perfect. So this is a sketch from our paper, but the images, I think everything else seems fine. It's just that TB, I think. Okay, I think that screen is still loading, but you're probably all looking here, so I think I can continue. I'm assuming that I can continue, that I can hear the mic well, so it's probably all being the same recorder, right? Yeah, probably. It's all good? Perfect, thank you. So this image is this is a sketch from our paper, but these images on the top, they come from the group of Peter Bruce in Oxford. So it's a very strong group in solid-state battery. They have a very big battery project there called SolBat. And what they do basically here is that they do this synchrotron imaging where they can see how this interface evolves. And these are resolved for sodium because there's a lot of interest also in sodium batteries, but the behavior is the same as you see in lithium batteries. And what you see here is that because the interface is never perfect, it looks almost perfect, but it will never be perfect. You see there's a small defect here, you'll always get some sort of non-uniform flux. So the interface will never be perfect. Because the interface is not perfect, then every time you discharge your battery, you do stripping. Basically what happens is that you are removing sodium or lithium, it's the same. You're removing some lithium from here. Ideally, you should remove lithium, in a uniform thing. So ideally, you want to have. So if I look at the lithium metal solid electrolyte, when I do discharge of my battery, when I do stripping, you should remove something like this. And then when you do charge your battery, you do plating, lithium comes back in. You plate lithium back. That's the idea. You strip lithium or you plate lithium. However, what happens is that this doesn't happen uniformly because the interface is never perfect, it's never uniformly. So what you see is these voids that you see here. You see these very big voids, coalescence of multiple voids. And those voids grow when you do stripping because you have some sort of concentrated stripping, so localized removal of lithium. So you get these voids. And when you do plating, when you deposit back the lithium, you see that you close a little bit those voids. So this is the 11th stripping, this is the 12th plating. So this one came after this one. You see these horrible voids became a bit less horrible, they're still there, but they became a bit less horrible, and they even occluded the void, so one of the voids is separated from the interface. And these voids are critical, because whenever you have voids, you have a big change in conductivity, which means you're going to have what they call current hotspots. You're going to have very small regions at the edges of those voids where the current is going to be very large. The current density that you have is going to be very, very large in the electrolyte. And because you have this very large current, you're going to accelerate the deposition of lithium during the plating, during the subsequent plating, and therefore you're going to form those dendrites. This is the issue. So you do strippings. This is the 11th one. Eventually, through stripping, you get these voids, and then you generate these current hotspots where the current localizes, and then when you reach a critical current, you deposit those dendrites, and then those dendrites, again, there's no way you can stop them. This is the issue. So we thought, okay, if we can model the conditions in which those voids form and evolve, if we can simulate those current hotspots, then we will have a tool that will let us know under what conditions those dendrites will form. And then we're not going to simulate the growth. People have used phase field to simulate the growth of the dendrites, but we're not going to simulate the growth. We'll just say, a dendrite has formed, bad news for your battery. This is the idea. So again, this is a kind of complicated problem because, you know, there's some mechanics. There's actually a lot of mechanics. I haven't discussed mechanics that much so far, but the main hypothesis in the battery community to solve this problem is to use a stack pressure. So they say if we apply a pressure, since lithium metal is like a toothpaste, we close those voids. This is the idea. So lithium metal, you know, is viscoplastic. There's some creep phenomena, so you could apply a pressure. In principle, you know, you get an equilibrium solution, you get a distribution of the material, and you may close those voids. So there's a lot of mechanics because, yeah, again, the main strategy from the battery community is to try to close those voids with mechanical pressure. He said, again, a couple electrochemomechanical phenomena. You have, you know, electric fields. You need to predict how the current arises there. And, you know, they have a lot of chemistry. You have the stripping, the plating, somewhat similar to corrosion, right? And then you have the transport of lithium within the metal. So again, a couple problem where, again, you have an interface evolving, the voids. And you don't need to, this is a different problem. We're not dealing with cracks. We're not dealing with corrosion. We're not dealing with, the interface that matters here is the void solid metal interface. So my phase field needs to describe it. So again, when we look at this problem, we thought, okay, this is a good problem to solve with phase field because we have an interfacial problem, things are evolving in time, and we have an electrochemomechanical problem. So I'm going to tell you a little bit of how we develop a theory for this. I'll spend time in each of the ingredients. But just to provide a sketch, this is the physical phenomena that are happening in this problem. So anytime you do stripping, well, in any case, you always have some sort of vacancy diffusion. So lithium atoms moving within the metal, so some sort of transport thing. Then you have the stripping process. You remove atoms, so similar to corrosion. You remove lithium atoms, and you generate voids. This is when you remove enough atoms, you have this coalescence of vacancies, and you generate a void. That void is going to evolve in time. When you do plating, is the opposite effect. So you are depositing those lithium atoms back. You also get the transport of vacancy diffusion. And then eventually you occlude those voids, you close those voids if you deposit enough. You have annihilation of vacancies, basically. And then what you have is also the mechanical effects. And there's two types of mechanical effects. One is the distortion of the lithium metal, the lattice, due to the vacancy diffusion. So this is very similar to the chemical strains that we discussed before. And the other mechanical effects is that you have a lot of creep and deformation in the lithium, and that you're applying a pressure, a mechanical pressure, to try to close those voids. The goal here is that they want to apply stack pressure throughout the entire thing. So they cannot control, if you think of a battery cell, it's very difficult to, it's not like having an instrument machine where you can say, oh, I'm going to apply this. So they basically come up with ways of applying a stack pressure, holding things under pressure. And so it will be under pressure at all times. And they're hoping that this pressure, due to the creep, will close those voids. This is the goal. Yeah. So this is the goal. So let me tell you how we capture each of these ingredients. And I'll tell you with some maths as well. I hope it doesn't become too dense. You don't need to, of course, understand this math. It's just for you to get a taste of how one will build a theory like this. But first, you know, we need to capture the interface reaction, so those atoms being taken away or being deposited. That we do through appropriate boundary conditions. You need to capture as well the vacancy diffusion, so, you know, a transport equation to capture how the lithium moves within the metal. Then you need to capture the voiding. For that, we use the phase field. And the physical mechanisms here are the nucleation of those vacancies, the coalescence of those vacancies, or their annihilation. This is how voids grow and shrink. This is our hypothesis. And then you have the mechanics, which is the lattice distortion and the creep. So let me tell you how we build a theory for this. So basically, we need to describe these domains. So we come up with a phase field variable. In this case, different to the previous literature, I'm going to call the phase field psi. It's not going to be phi. It's going to be this psi parameter. So this psi will be equal to 0 in the void and equal to 1 in the metal. And then the interface, of course, is going to be a smooth interface. So this psi parameter is going to be between 0 and 1. So you have various interfaces. You have an interface between the void and the metal. And the void might be located at the interface between the electrode and the electrolyte, which is the purple interface here. Or it might be, you know, occluded inside of the metal. And then we can define various quantities related to lithium transport. So you have some lithium occupancy. We have some concentration. So if you take these volumes to the extreme, you take the limit, you get that, you know, the number of lithium metal atoms divided by the volume of atoms, it will be the concentration. The backhand size will be the density of vacancies, basically, taken to the stream. The lattice size will be the occupancy of lithium within those lattice sites, and then finally the occupancy of lithium will be the concentration of lithium within the number of lattice sites. This is the idea. So these are standard definitions of transport. Then you have the Boyd evolution. For that we use a phase field model, type of Allen-Kahn type of model. So in the lithium metal we will have the situation where the phase field is equal to 1, and those species, those occupancies are going to be equal to 1. And in the Boyd we have the situation where we have no concentration of lithium, no occupancy of lithium, no strain density, and then we interpolate in between using some sort of interpolation function. So again, it's up to you. We play a little bit around with these functions. We took some of them that were familiar in the literature, but also took a look and see whether we needed to capture additional phenomena. This seemed to be fun enough. Then you have the mechanical behavior. So you have some chemical strains related to, well, you have elastic behavior. That's not complicated. You all know elasticity. So again, this situation where you have Hooke's law. The only thing you need to take into account is that when I'm using this subscript, G, what I mean is that I'm interpolating, of course. There will be no strain and density inside of the Boyd. So these quantities will be interpolated. Then you have the chemical strains. So again, this is based on lattice distortion, similar to what we saw before, some difference in concentration. And then you have viscoplastic strains. For this, we use Anand's Crib model. And there's data. Okay, I'll tell you about a bit more later. We have a slide, I hope, where we show how we can fit the parameters of the Crib model to test on lithium at different strain rates. And then basically you model the Gibbs free energy. So you formulate your Gibbs free energy. Again, no need to understand this in detail, just for you to see the steps. You take the derivative to come up with the chemical potentials. Then you define the bulk, Helmholtz free energy, and then a Helmholtz free energy that accounts for the interface and the bulk. So you can divide them both contributions to the Helmholtz free energy. This, standard, I would say, continuum mechanics. For some of you, this will be familiar. For others, it will be a bit maybe on the advanced side of things. Nothing to worry about. This is just the way you build these theories. Then we are dealing with the theory of lithium transport. So for some of the constitutive choices, for the lithium transport, as I said, is very straightforward. Similar to the hydrogen, you have a chemical potential, you have a concentration, a kind of extended version of Fick's law, where you have a concentration, a change in concentration. It's basically modeling substitution diffusion. These are, by the way, the boundary conditions, so you may have a flux on these locations. Then what is important here is that you have a lithium transport equation to simulate the vacancy diffusion, and you have some interface reactions that will capture what's happening in the plating and the stripping, basically. So you change the sign, but basically you have this relationship, and we have enhanced this to account for Butler-Borman as well, but it's the same idea. You have a current. This current will be going in one direction or the other direction, whether you are applying stripping or plating, and this will change the flux. So there will be a flux being applied on your interface. And if you want to start with a perfect interface and want to simulate a non-ideal interface, like it happens in reality, you'll make your flux to be non-uniform, for example. Then we have the Boyd evolution. So this is all based on phase field, so non-conserved quantity, Allen-Kahn type of equation. Again, you may remember that it seems familiar. It's slightly different because of the way we derive these models, but you may remember a few items. You see the L and so on, a few items that resemble much more the solidification corrosion models. And then the mechanical problem, you interpolate again with the phase field, so you degrade. There cannot be any load carrying capacity inside of the Boyd, but otherwise it's very similar to before, and sometimes we apply pressure, sometimes apply displacement, those boundary conditions. In terms of the mechanical behavior, the constitutive behavior is described by Anand's viscoplastic model or Crib model. It's a very simple type of power law model where you have an exponential activation energy and a flow resistance rate. It has a number of parameters, but the good thing is that we have experimental data of lithium, pure lithium, and the different strain rates, so we can feed those parameters of the Anand model, the constitutive parameters to the data. So the same way you will fit, of course, yield stress, hardening exponent. So that's I guess the takeaway. So we have a well-calibrated model. And then the other thing is that we not only model the anode, we also model the electrolyte, because we want to capture those current hotspots. So we're going to solve an electromechanical problem on the electrolyte. So we're going to solve for Ohm's law. We're going to solve here. You see the equations here. So you solve the electrical problem. Careful here, sigma. We use sigma because this is the notation in the community. In both places we solve the electrochemomechanical model. But of course, the one that is distressed is the one that has no subscript and that is in bold because it's a tensor, right? So anyway, you solve in the electrolyte. We don't have plasticity in the electrolyte. It's purely elasticity. It's a ceramic. And then you solve the electrical problem as well, where you are interpolating the conductivity with the phase field, because there's no conductivity here in the voids. And that change in conductivity is going to make the current density change dramatically. This is what triggers the current hotspots. But this is basically the boundary conditions and the problem that you're solving for. So just to summarize, the model has a number of ingredients. First, we have bulk and surface substitutional diffusion. That is done through a hydrogen transport equation that is coupled with the phase field. We do capture faster transport through the surface thanks to these terms. So I think that's also relevant. They do see faster diffusion through surfaces. We capture that through the term. The dissolution or the position of lithium. This is captured through appropriate boundary conditions. So we have a flux that is going one direction or the other, depending on whether you have plating or stripping. The voiding process, the evolution of voids, which we assume is due to vacancy nucleation or annihilation, that is captured through the phase field model. And all the couplings come to this derivation of the Helmholtz free energy. And then the creep model, the mechanical behavior based on creep, where we have found, we calibrated those parameters based on experiments. And finally, you have the hotspot formation, so the formation of the accumulation of current, the distribution of current within the electrolyte, which we capture by solving the electrical problem and by noting then the conductivity is going to be different inside of voids and the metal. And that's the key point where you will see this, where in reality you see these hotspots. If everything is uniform, everything is great. But the moment you have a void here, the conductivity inside of the void is going to be 0. Here is going to be the one of the lithium metal, so you're going to have an accumulation of current there. This is the issue. Okay, so this is the boundary value problem that we solved. Just to start with a very simple one, we start with a very simple void. We apply plating of stripping, discharging or charging or discharging, and we see what happens with that void. And here you see a summary of the initial conditions, boundary conditions, and also the governing equations. So again, in the lithium metal, the degrees of freedom that I'm solving for are my phase field, which I call chi in this case instead of phi. This is the notation that the battery community, solid state battery community, are using. So this is what I'm solving for in the lithium metal. That's 1 degree of freedom. Second degree of freedom is concentration of metal ions. Then you solve for the electric field, the displacement problem. So in this case, it's two-dimensional, two components, and then the electric field. So we have essentially 5 degrees of freedom per node in the lithium metal. While in the electrolyte, we have this interface condition. So depending on your current, you're going to be applying a flux. And you're solving 2 problems. The mechanical one, so 2 degrees of freedom, and the electrical one, 1 degree of freedom, so 3 degrees of freedom. And the boundary conditions are quite important. So the boundary conditions that you get is, of course, some continuity conditions here. You are applying a current here at the edges of the electrolyte, which is, by the way, a ceramic, LC0. You are applying a current here. So this current will change signs, whether you are doing stripping or plating. You will predict a distribution of current. Based on the current, local current, you'll get a flux on the edges, and then that's the connection between the 2 pieces. And that's important because I'm applying here a current in one direction or the other. This will translate into a distribution of current. This distribution of current will change my flux, and that will capture exactly what's happening in reality. So some representative results. Again, one single void, stripping. So now I'm discharging my battery. Where you see on the left side, so I'm plotting the 2 domains, the electrolyte on the right, the lithium metal on the left. I start with a void, and I see how the void grows. So this is phase field on the left. So the chi variable is phase field, so it goes from 0 inside of the void to 1 in the metal. And you can see that it varies smoothly in between. You can look at the interface. On the right, in the electrolyte, I'm plotting the normalized current, so the local one divided by the applied one. You can see very nicely the distribution of the current, very nicely how the hotspots are captured. And I mean, in general, you can see that the behavior is at least qualitatively what we see in the experiments, right? We see the void that is enlarging due to the application of stripping. We are not telling the void where it has to go. Again, this is just solving a phase field problem and minimizing that functional, the void decides where to go. You can see that the current hotspots are arising naturally. I don't have a criteria to define where a current hotspot nucleates or not. Just They are rising naturally there. So you see exactly what you expect from experiments.
Just a small clarification, Emilio. In this entire problem solution, concentration is not a field variable one is working with, right?
Concentration is a field variable. Yeah. So we have 5 field variables. We have the phase field for describing the evolution of the voids. You have concentration to describe the lattice diffusion, so the vacancy diffusion. Then you have the deformation problem, so a couple of, in this case, UX, UY, 2 displacement components. And then you have the electric field. So in the lithium metal, in the electrolyte, there's no concentration. Yeah.
Yeah, so that was what I was kind of trying to ask.
Okay.
The dissolution of your metal, the lithium in this case, is Ohm's law based, right?
Yes, exactly.
So in that case, one doesn't need to do what you had.
Exactly. The connection comes from the current, so you have a distribution of current. The current will dictate the flux here, and that's all. Yeah. So you don't know anything about the flux until you get to the interface. Yes. So you see that it's qualitatively seems to agree well with experiments, and the model can naturally capture how the void evolves and how these hotspots appear. So then you can, for example, come up with a criteria where, based on an experiment, you say, my dendrite is going to grow whenever my hotspot reaches a quantity of 3.5 or whatever, and then you do that. And you can see, the shape of the void seems to be relatively similar to what we see in those experiments that I showed you before, right? So, I mean, I'm rotating again things, so this is horizontal, what I'm plotting now vertical, but you can see the shape of the void doesn't look too different from what the model seems to be predicting. Oops, sorry. This is plating, and then, this is after several times, so as a function of time and whatever applied current you are doing, whatever charging conditions, discharge conditions, you can see how the void is evolving. You can see how those areas where your current exceeds a critical quantity are growing, and you can see that it resembles more or less the experiment. So things seem to be going well in the qualitatively. Now we go to plating. Again, same type of results. On the left, the lithium metal anode, showing the phase field from 0 to 1, 0 in the void, 1 outside. On the right, the normalized current. And you can see how the void is closing as we deposit lithium, and how eventually you get completely occluded from the electrolyte and your hotspots disappear. So this is the plating. Again, what I think to be in good agreement with experiments, right? If I go back, we saw this plating. You can even see the occlusion of the void. The void is separating completely from the interface, like this one. And we saw that in the experiments too. So again, qualitative behavior seems to be quite good. And you can see here some representative results after multiple hours. You can see the hotspots being quite strong here, almost being eliminated after 1 hour and then going away. So the model seems to qualitatively agree with what we're hoping for. Then we use the model to try to interrogate a few things. So this is the effect of different applied current. So depending on the current that we apply for a fixed time of 1 hour, you can see stripping or plating. If you increase your plating or stripping current, of course, you see voids growing more or less, and so on, as you would expect. We also try to understand the interplay between creep and diffusion. And there were some experimental evidence suggesting that creep dominates over substitutional diffusion. We saw that this was the case. So you can switch things on and off, basically, and see which one dominates. And then, of course, we not only limited to model a single void and one cycle, but we can model multiple cycles, multiple voids, a much more realistic representation of the interface. So this will be the problem. The more extended problem is, the balance equations are the same. I rotated again my battery, but I hope that doesn't confuse you. So now the lithium metal is on the top, the electrolyte on the bottom, same in boundary conditions, but now I'm going to add some voids, and I know from the manufacturing what are the scale of these voids. So I'm going to add those voids, and I'm going to solve the problem, and I'm going to do multiple cycles of plating and stripping. I can do with pressure, without pressure, so you can see here those voids growing and diminishing in size with the plating and stripping, and then I can do that. This is in the absence of pressure, so you eventually see some voids vanishing. You can capture the complete vanishing of some of the voids if your plating cycle is large enough, and then you can also do that with pressure, so you can compare without pressure and with pressure, and you can see how, for example, these voids are starting to merge and shrink, and with 1 megapascal you can see much more pressure, how those voids are disappearing altogether. So again, this is the kind of takeaway. You have a tool that allows you to simulate all the conditions, and realistically, you can see what pressures you actually need in order to to make those voids disappear, and so on and so forth. Yeah, so this is what you're seeing. You see some hotspots there. You see the coalescence of voids where the hotspots disappear. All these phenomena can be captured with this type of models. So you have a virtual platform that will tell them, and this was our idea from the beginning, right? It's unclear under what conditions a solid-state battery breakthrough will be possible. So we were trying to map those conditions, and then it's up to an engineer or a CEO of a company to decide whether it's worth pursuing that route or the regime of feasibility is too small. Yeah, you can see how the voids vanish after 1 megapascals. And now some of the things that we're working right now, this is kind of permanently ongoing work, because the student who finished now Runzi 1, he's been hired by CATL, which is the biggest battery manufacturing company in the world. It's in China, and they have a solid-state battery group, which they do actually quite advanced research. And he stopped his thesis before he published his last paper, and he's working now with them. So I don't know whether this paper will ever see the light of day. But you can see that we're trying to go towards more quantitative virtual experiments. You can see voltage versus time. We can see this kind of voltage localization, and we can see this is for different applied currents, experimental observations, and finite element predictions, and we seem to be able to get a very good agreement. And this is the active area ratio. So basically they see how much voiding they get for different applied potentials in the experiments, and they see how those voids evolve as a function of applied current, and we can see that we seem to be getting good agreement with the experiment. So I think that so far I showed you qualitative results, but it seems that the models are also able to do quantitative work. And then one last item that I want to discuss, so we may finish a bit earlier today, which I think is fine after such a long week. You'll probably appreciate it. But one last item that I wanted to discuss is what are called anode-free batteries. So solid-state batteries will be the next breakthrough, and within solid-state batteries, what people are hoping is that we'll have anode-free batteries, which will be batteries where you start with no lithium metal in the anode. So we remember the picture I showed at the beginning. I'm going to rotate it, so you have lithium metal here, you have an electrolyte, and then you have the cathode here, and then you basically strip, so you take lithium out away from here, or you deposit lithium. The idea is you can reduce the weight and there's other advantages. If you can eliminate your lithium metal anode, you start like this, and then you do a first plating, you deposit some lithium, and then now you continue to do your battery behavior. That is the idea. This is what they call anode-free batteries. So this is work we did with the group of Matt McDowell at Georgia Tech. And basically, again, I think all solid-state batteries with a lithium metal anode are tricky. Without the lithium metal, it's even more tricky. And the reason is that, as you can imagine from the discussion we have so far, you want the interface to be perfect. The moment the interface deviates from perfection, then you have a problem. So there's a lot of discussion, for example, on how to either applying a pressure, but also changing the geometry, improving the manufacturing so that you don't have any inclusions at that interface. It's as perfect as possible. Some people also say that, I think there's a company in the US who claim they have a new patent where I think they put a layer of gold or something like this. So you do things to make sure that your interface remains as constant, as uniform as possible. And here the challenge is that when you plate the lithium in the first place, you need your lithium plating to be perfect, basically. That's the idea. And yeah, as you can see, this is some sync control measurements. That plating of lithium is far from perfect, and we can show with our models that lack of that inclusions of those extrusions that appear there, the lack of perfection in the lithium plating is what leads to those voids and those short circuit of the battery. That's all on the batteries, so it was a bit shorter, but any questions so far? If not, I think it's the end of the course. So yeah, well done in making it all the way here. It's been a pleasure to engage with you. It's always a pleasure to teach to an audience that is interested, that is always asking questions, that is approaching on the breaks to clarify things, to see how the things they saw could be applied to their problems. So it's been really a very productive week, a very enjoyable week. And first time in India, I also enjoyed the personal experience as well very much. And now I can eat the spicy food finally after 5 days of training. So yeah, it's been great, and I look forward to seeing many of you. I hope that your paths and my path cross multiple times in the future. Either you'll be coming to Oxford, or we'll be seeing each other at conferences and other events, and who knows, maybe we'll collaborate in the future or have projects together and so on and so forth. So yeah, a pleasure meeting you all, and looking forward to seeing more of you in the future. Thank you.
Thank you, Professor, for all the patience.
No patience, no patience. Thank you guys. It's always, if no one asks any questions, that's the wrong sign. That's